Okay, we're on part 4 of the chapter 8 discussion, conceptual physics, chapter 8. And we're going to talk about centripetal force, a force directed toward a fixed center of rotational motion is called a centripetal force. So you can see this young lady spinning this can around her head. What's supplying the centripetal force? Well, it's the string. It's the string, the tension on the string is supplying the center-seeking force, the centripetal force, on this can. So whenever there's any kind of centripetal force, a center-seeking force, there's going to be something pulling the object towards the center. The sun is pulling the Earth towards the center of its rotation. It's not really a circle; it's an ellipse, but that's okay. It's the gravitational pull of the sun that keeps the Earth in an almost circular orbit. It's the Earth's pull, the gravitational pull on the moon that keeps it orbiting around the Earth in an almost circular motion. So a centripetal force is a center-seeking force, and we'll learn that there's a centripetal acceleration that causes the centripetal force. Okay, so example: to whirl a tin can that at the end of a string, you pull the string toward the center and exert a centripetal force to keep the can moving in a circle. So the string is what is supplying the centripetal force. So centripetal force depends upon the mass of the object, the tangential speed of the object, and the radius of the circle. So in words, in equation form, the centripetal force equals the mass times the tangential speed divided by the radius. Now, let's centripetal force is this is it in equation form, this one. You remember, force equals mass times acceleration. Well, it so happens that the centripetal acceleration is the velocity, the tangential speed squared divided by the radius. That's what it says here, tangential speed squared divided by the radius. So if the centripetal acceleration is v squared r, then for the centripetal force is equal to mass times acceleration. That's equal to mass times the v squared divided by r. That's what provides the centripetal force. Okay. When a car rounds a curve, friction forces on the tires act centripetally, carrying the car along the arc of the curve. If the road is wet or if the car is going too fast, frictional forces are insufficient to act centripetally, so the car skids off the road. Let's say you're driving in a car and you're a passenger in the car. The person driving turns to the left at a high rate of speed. You feel yourself going against the door on your right side. Now you've got your seatbelt on. You know, at least you should. If the door were to fly open and you didn't have your seatbelt on, you would fly out the door. Now, people, I'm jumping the gun a little bit, but they think, well, there's a centrifugal force that's forcing me out. It's not really. It's your own body. Remember the back in chapter 2, we talked about inertia. Your body wants to go in a straight line motion. Well, it's the seatbelt and the door that are providing the centripetal force keeping you going towards the center. The tires on the road are also providing it, but they're providing the centripetal force for the car. But it's your seatbelt and the door that are providing the centripetal force on you. Okay, let's suppose you double the speed at which you round a curve. By what factor must the centripetal force change to prevent you from skidding? Now, let's go back up and look. If you double your speed, v squared is if it's 2v, then v squared is 4v squared. So if you suppose you double the speed at which you round a curve, by what factor must the centripetal force change to prevent you from skipping? It has to be 4 times. 4 times. Since the centripetal force depends on the square of the tangential speed, doubling that speed quadruples the centripetal force. Okay, after rounding one curve, you enter a sharper curve with half the radius of the curvature. If you travel at the same speed, by what factor does the centripetal force change to prevent skidding? Well, up here. The radius is in the denominator, and there's no squared term. So it doubles. If you travel at the same speed, by what factor must the centripetal force change to prevent skidding? It doubles. Since centripetal force depends inversely on the radius of curvature, having the radius doubles the centripetal force. Okay. Now centrifugal force. All of this time I've been saying centripetal, center sequence, centrifugal force. Although centripetal, let me dismiss this since it's hiding some of the text. Although centripetal force is center directed, an occupant inside a rotating system seems to experience an outward force. This apparent outward force is called centrifugal force. Centrifugal means center fleeing or away from the center. It is a common misconception that a centrifugal force pulls outward on an object. If the string were to break while you're spinning this, the object doesn't move radially outward. It continues along a tangent straight line path because no force acts on it. That's Newton's first law. So centrifugal force, as I was saying, you ever got on that carnival ride? I don't know that they even make it anymore. It's a cylinder. You get in, you step inside the cylinder. It spins you, and when they drop the floor, you're pinned to the wall, and you think, oh, it's the centrifugal force that's pinning me to the wall. It's really your own inertia wanting to go in a straight line, but the wall of the amusement ride is making you keep in a circular motion. Think of a washing machine. The washing machine has holes in it. For when the spin cycle occurs, it's spinning the clothes. They're flung to the end because they want to go in a straight line, but the wall is holding them in. The water, with all the holes on the side of the washing machine drum, it's free to exit. The water exits, and that's what squeezes out the water from the clothes in the spin cycle. Okay. Rotating reference frames. Now, centrifugal force experienced in a rotating reference frame seems as real as other forces. Example, the bug senses a pull toward the bottom of the can. He's feeling what feels like gravity, but it's the centrifugal force. Even though it's not a force, it's a real effect. He's feeling like he's being pulled towards the bottom of the can. You can take a bucket of water, and if you swing it fast enough around, the water will stay in the bottom of the bucket. People say, well, that's centrifugal force. Well, the water wants to go in straight line motion, but it's the bottom of the can that's keeping it inside the pail. Okay. Centrifugal force can be used to simulate gravity in space stations of the future. Anybody ever see this 2001 Space Odyssey? They show a guy running around a circular space station. It's spinning fast enough that he feels a sense of gravity. By spinning the space station, occupants would experience a centrifugal force, simulated gravity, similar to the bug in the can. Okay. To simulate an acceleration due to gravity, g, which is 10 meters per second squared, a space station could have a radius of about 1 kilometer. That's a big space station. A radius of 1 kilometer, that's a diameter of 2 kilometers. And it would rotate at the speed of about 1 revolution per minute to simulate uh, artificial gravity. Okay, and that's the end of part 4.